matter what, I'll keep on talking. We can catch up with the slides later on. But we had, a pretty long discussion on our state-of-the-art report that Mohammed presented. And, long meeting and so on. And after about 3 hours in that meeting, we get to new business, and there is no presentation. All right, there we go. Finally. All right. And Nick van Hoof came to the committee with new business, like, hey, why don't we run a new round robin test on concrete rheometers? I'm like, yeah, it's a great idea. It's not in the scope of the committee, but if you can find somebody crazy enough to organize it, for sure we'll go with it, right? And Yannick and Shafika, they volunteered to take the lead onto them, and we were all very happy with that. But maybe the first thing is what is the round robin test, right? The round robin test is a test you do in multiple places, multiple laboratories, independently to try to assess the results and see how much they vary from place to place, right? So typically what you do, you send a sample around, and everybody's going to test a sample with whatever test they need to do. In fresh concrete, though, it's a little more difficult to send a sample around. You can't really do that. So we have to think around the system a little bit, and instead of, you could explore different ideas on how you're going to run robin tests on concrete rheology. What you could do is tell everybody, you make a specific concrete, you make it in your lab, you put it in your Rheometer, let's compare the results. However, results are dependent on constituent materials. Cement, and I'm picking on cement, but everything else as well, right? The cement is different in Orlando, it's different in Chicago, it's different in France, and so on. So that's not really going to work. Second thing you can think about is like, okay, if there's really so much influence of constituent materials, why don't we take a whole batch of cement and a whole batch of aggregates and a whole batch of admixtures and send it around the world? Have everybody, again, at their own place, test the rheological properties. Here's the issue. The rheological properties also depend on your mixing energy. They depend on your climatic conditions. So whether Kamal and me make our concrete back in Missouri or Sofiane makes it in Clermont-Ferrand, it's going to have different properties. We can't require everybody to have the same mixture and to have exactly the same concrete. So we want to reduce that variability as much as possible. So, if you can bring the concrete to the equipment, you bring the equipment to the concrete. And that's what we've done. Right, so 29th and the 30th were the 2 days of intensive labor. So we had 20 hours of work, physical work, and people in the industry could be used to it, but those as academics, physical work is a little tough, I can tell you. Right, so now a couple of things to think about if somebody gets it in their mind to organize something similar is preferably you do this at a location where you already have a couple of devices, right? And at the University of our host institution, they had 4 devices available for us to use. And then people come from close by or far away with some equipment as well. So we had Schleifinger come over with this Excel, the EBTM Schleifer. We had Ekium, Clermont-Ferrand, and Ghent University coming in Rijker. We had then student Arnaud over here coming up with playtest, and our contribution from the United States with a little extension on that on the Rijker. That's what fit our suitcase. So that's how we brought everything together to perform the work. You also do it in a place where you had a lot of space and a lot of people, right? So in total, we were 17 collaborators that afterwards have worked together into discussing the results, analyzing the data, coming to conclusions. And we had the help from one technical staff and 7 student members from around in that place. So critical mass is essential. You're not going to run this by 3 people. It's not going to work, right? And here's maybe, in my opinion, the most critical one. You need a concrete producer that know what they're doing. Because yes, there were discussions ahead of time on like, what kind of concrete do we want? But there were a lot of discussions the day before and the day off. Like, okay, now we got concrete number 1, now we got concrete number 2. We got concrete 3 to be number 3 really different. And concrete 3, SEC 3 was not planned. We actually had a discussion while we're testing concrete. It was like, now we want something sticky. And then you need to have a ready-mix producer that knows what they're doing. And with Ekium, we had the lead of Fabrice. It was absolutely perfect. We challenged him to the nail. We gave him big, tough tasks, and they fulfilled the task. And without this, we wouldn't get very well. Financial support. There's a lot of coffee to be had during days like this, but then with the dinner and the entire organization afterwards. So we're grateful for sponsorship from local French associations, even from private company, and then the university and the lab itself in the region to support this event over there, because without financial support, it's going to be a little difficult as well. Now, how do you plan this thing? And again, to go with the question from the knee and so on, what has evolved since the early 2000s? So the first thing is that we get more flowable mixtures because all the developments in the admixture industry and so on. The second evolution we have is we think, let that claim in the middle, but we think we know better what we're doing. We know better that how can things go wrong during measurements compared to that period, because we get 15 years of research experience behind us and a whole bunch of literature. And I want to really want to put this out in there, is because our scope was trying to go as far as possible. We didn't go as far as possible. We had 20 hours of testing to do. We had 8 mixtures. And what we wanted was to maximize the number of valid results. We had 17 people working on this, slaving themselves out, having back pains the next day because they're no longer using on 12 hours a day, physical labor. And then you have to tell them afterwards, like, hey, you know, half of the results because of this and this and this issue, they're invalid. We can't use them. So that's something we try to avoid as much as possible. So we try to play it safe as much as possible and still have a large variety of results. So that's where we some things that we're going to discuss here. We also try to exploit the concrete as much as possible. Have different types of measurements, as Mohammed explained, and try to get multiple measurements on the same mixture in at different amounts of time, so we can generate as much data as possible coming in. So to reflect on that incorrectness and that invalidity of measurements, there's a couple of things we considered. And your measurements, and that's why we won't have an universal rheometry, it won't happen, right? Your measurements can become invalid because of the mixture and can become invalid because of the measurement. And the main issue with concretes is it's a mix of a little bit of liquid and a lot of solids. And depending on how these interact, you may get completely different behavior. You may have the standard suspension rheology behavior for the more fluid mixtures, or you may go with friction. And the interpretation changes completely. There's no viscosity in case of friction because you're shearing in a preferential shear. It's like a soil. It's a granular material. So if that will happen, then our viscosity measurements are totally useless. Right? So we try to avoid friction as much as possible. Then we get the migration and the segregation issues, where particles are moving down or particles moving sideways. That completely invalidates the measurements. We need to avoid this. So the way we bend is to have a stable mixture, but yield stress on itself is not enough because we're flow, so we exceed the yield stress. So we need to have a decent viscosity and try to avoid large aggregates as much as possible. And then what we also can have is extensive flow, because all rheometers we use, apart from the interface ones and the plate tests, all other rheometers were concentric solid related. Which means if you have mixed with a really high yield stress and really low viscosity, you're going to get a very small sheared zone. And if that sheared zone becomes smaller than one aggregate, are we still measuring concrete? We aren't. So that would also invalidate the measurement. So, and these are things we can't go around. If it happens, it's done, game over, right? And then we have a couple of things related to the measurements, right? And one of the first measurement artifacts discovered was the non-equilibrium. So your properties could be evolving as a function of time during your measurement, which you don't want, right? Solution for that is actually have an appropriate duration of appreciated periods, which we judge based on our experience. Plug flow itself can be corrected for. There's an iterative procedure that exists for that. And then to limit particle migration, you can try to limit as much as possible the duration of the measurement. We actually will have next presentation, just to keep you here. We'll have some very interesting results in that. So the conclusion for our mixtures was to have flow mixtures that have a reasonable amount of aggregates, but not too many, so we'll avoid that frictional condition in there. So as a conclusion, we did not test conventional vibrated concrete. And you can tell us, okay, you know, you didn't go far enough. Yeah, fine, I'll accept it, right? But it's just to be safe as much as possible going in there. And then we had 3 mortars we evaluate because aggregates are a source of the problem. So if you don't have the aggregates, are the results actually going to be different? Is our comparison going to change if you look at mortar and concrete, or is it all going to be the same? Right? So we have a couple of reasons why we tested mortar as well. So Mohammed presented the mixtures. Here you get them again. So we get a reference self-consolidating concrete coming from APM. Add a couple of variations on that to lower yield stress to increase viscosity. Then we had a flowable concrete mixture that has less powder, more aggregates, but not to the extreme. That we modified once, and then we had 3 mortars that were evaluated, and those results will come back throughout the coming presentations. Everything was prepared in a central batching plant and came in one truck to the location. And the advantage of that is that you don't have any batch-to-batch variability. Imagine you try to make this in the lab, you need to make a quantity of concrete that you need to batch 3 times. Batch 3 times, who says that the third mixture is the same as the first one? I'm not going to put myself on the line for that, right? So to avoid that problem and then having to mix up those 3 different batches to make something uniform, which is not that easy, the truck gives us 1 batch. And we know we don't have the batch-to-batch variability there, right? Some mixtures, we adjusted them on the fly, on site, which was a challenge because the company wasn't used to that. Here in the US, like, yeah, let's throw in some more fat mixtures, fine. In France, it was a little more of a trick. There was a little more, we really had to do some convincing to make sure that we're going to do this as well. And then once the concrete was to our desires, that the workability we wanted, visually, we did some first tests to see what was going on. We kept 6 real barrels and we tested that. So we measured, as Mohammed said, 3 different kinds of measurements. We measured flow curves with all these devices in there, but we had 6 devices that could get everything into fundamental units, and we had 3 devices or 3 configurations that led us to be in relative units, which we cannot transform into yield stress viscosity because the flow pattern is too complicated. Structural buildup, we had a couple of measurements, and Sufyan will tell us more about structural buildup. And then the interface properties, we're not really going to discuss this because the investigation is still in progress, running into some issues. I'm trying to compare or trying to see why it shouldn't relate. Theoretically, there might not be a relationship, or there should not be a relationship between the resistance to pumping and then the resistance to friction. So this is the overview of the time frame we looked at. So time was not really in our interest. Whatever happened before the first test, we didn't really care because we just wanted to look at every time frame, can compare properties. So all our rheometers, they could measure flow curves, measure 3 flow curves during the tests. In between, a series of the rheometers measured static yield stress, and then the sample was undisturbed between the first and the second static yield stress measurements. And then the other devices could measure interface properties. So that's more or less for every concrete, the 80 minutes of hard labor, and then plus or minus another 40 minutes around. So about every 2 hours, we completed the full test with everything going on. So to more detail on flow curves, on the procedure of flow curves, and I really need to pay attention to this because that could be one of the reasons why things went wrong in the past, or when things were not that adequate in the past. So our procedure was, okay, let's appreciate 20 seconds at the maximum rotational velocity for concrete. Let's appreciate 30 seconds for mortar based on our common experience we had for measurements like that. We decreased the rotational velocity stepwise in 5 seconds, by 7 steps of 5 seconds. And the question is, what is the maximum rotational velocity you're going to impose? We really had some thinking on that the day before, right? So what's the limitation of the rheometer? What's the limitation of shear particle migration? Because rotating at 1 rotation per second is not a good idea, right? And then do we impose the same maximum rotational velocity for each rheometer? Maybe that's not a great idea because what governs shear dependency? It's not the rotational velocity, it's the shear rate. So what we try to do is match the shear rates in all the rheometers as much as possible. And the way we did this is use random equilibrium to our advantage, and we had a hypothetical concrete with a yield stress of 50 Pascal and viscosity of 20 Pascal second. So that was our virtual concrete that we use in our mind in our calculations. So what you see here is random equilibrium, but the opposite way around. So instead of calculating yield stress from G and calculating viscosity from H, we do the other way around. And the way we went is we looked first at the most limiting rheometer, which was the I-car in terms of rotational velocity, calculate GNH for the I-car. Then we can say, okay, based on our rotational velocity of 0.5 rotations per second, what's the maximum torque we apply on the I-car? And from the maximum torque, we can use the same equation as we use to transfer G into yield stress. It's a weighted average, it's an integration procedure to calculate the maximum stress. Once you know maximum stress, you know maximum shear rate, that is hypothetical concrete. So it's the same in every rheometry. And then we went the way back. We said, okay, this is maximum stress, now we impose on every single rheometry, all the other rheometers. And then again, the GNH from each of those rheometers and the inverted calculation to get the maximum torque, we got to maximum rotational velocity that we wanted to impose on each of these separate rheometers to get as good as possible based on this calculation, the shear rate to match as much as possible. So we thought this was a better process than just opposing constant rotational velocity. And here you got the results of that. And on first sight, it's like, well, that's pretty similar. Doesn't really matter. But if you look between the Rheocat and the ICA rheometers, that's a 15% difference. Might not be that negligible. Right? So that's how we changed how that we imposed the procedures. The minimum rotational velocity were just taken as ratios. We just said, okay, we'll extrapolate. We're too tired to calculate. The 4ACC rheometer, because it did not have fundamental units, so there's no way to calculate because the geometry is so complicated, we just picked what Oliver Wallach recommended. For the Rheocat with the helical screw on there, we said, okay, you know, it's about the same dimensions as the vein. Whatever works for the vein, works for the helix. We'll just copy those values as well. So this is the procedure. We applied the procedure before every measurement, empty. So if there's any residual torque value, we can eliminate it. Or for some other devices, we had a reset on the torque that was plane 0, so we don't work with those residual values that we had over there. And then what will come in the next presentation, we have one ICAR rheometer that followed a different procedure. And although initially we didn't like it, at the end we like it very much because it shows us something better. So what did we learn afterwards? The first thing we learned afterwards is that we need some kind of calibration. As you will see in the next presentation, the results are not perfect one-to-one. It doesn't happen. And we want to be able to attribute this to either calibration issues or flow pattern issues. And having a calibration material or having something that can calibrate rheometers or can measure torque and measure rotational velocity would have been very useful. We did have the NIST reference material, so for the record, thank you NIST, but we didn't have enough. Right? We had a little batch in there. It was sufficient to fill an ICAR once, but that used all our sample. And then we went a step further. We emptied the buckets, and then, you know, we get all the big beads, the 10mm beads, they're all coming out. But what's staying behind is the 1mm beads, it's all the paste. So we're changing the concentration of the particles by going from one measurement to the other. So it's not ideal. So we need to have like 5 batches of this material if you really want to do this. But that's something that should have been done. That's a lesson we learned afterwards. The second lesson we learned afterwards is that some things were decided the day before, some things were decided the day off, some things were decided half an hour before the concrete was made. It was a little tricky, right? So maybe, yes, and maybe no, because I'll have something at the end as well, the next presentation. All right, so organizing something like this is not easy. That's the main conclusion we want to, before we take it to results. It's a large undertaking and you need a lot of components that go the right way. You need to have the amount of space, you need to have a lot of people that are crazy enough to organize this, you need to have enough hands, and you need to have an active producer that's really going to be helpful and, you know, obey your wishes as much as possible. We tested 5 concrete 3 mortars to max out the output of the results. So we tried to have a little bit of a conservative approach to keep the validity of the results in there. And then, of course, we had contribution from the industrial partners that were really essential for the success of this. And this is where this one is going to stop. Thank you.
Thank you very much, Dimitri. We have time for some couple of questions. Yeah. David, please.
David Lang from the University of Illinois. So one of the unsettling things that we see in these round robins is that I guess it's not surprising that the rheometers won't give you the exact numbers with regard to viscosity, but they sometimes don't even rank a group of materials in the same order. Usually they do, but they don't always. And so what that opens up is the question of, well, what is really even the appropriate theory about what viscosity is and so forth. So let me give you just an example to explain my point. Let's say you're thinking about the ICAR rheometer and you have a flat paddle system versus rods of some sort system. And the fact that in one case you're asking the aggregate to sort of pass through the rods that are moving versus in the other case you're moving a mass of concrete and it's really shearing around the edge. There's a different kind of mechanics to it. So is there consensus developing in the community about what that needs to be for defining what viscosity and how to shear this material?
Consensus in the community, I would say no. I don't think we discussed it even. We didn't really look into this even from a community, from our committee point of view in that. Should there be consensus? Yes. Do we know from certain publications and literature that, the least veins you have, the more difficult it gets, and then the more you're going to force very high shear rates near the vein tips? We know that. So ideally, we should have more blades on our vein, but to say there's a consensus, no. Did we make new veins? No. Should we have? Maybe, right? So that could be a suggestion for future. If somebody's crazy enough to do that again, to see if you can change certain of those geometries and see if that would affect the results. That would be actually very interesting to say, okay, you put the Icar vein in there, and then let's fabricate something that looks slightly different. Let's put it in exactly the same hardware. That would be absolutely fantastic. The issue you have is how much does it currently change the function of time between changing out the samples, because you have to refresh your sample. You can't just say, okay, plop it out and then plop a new one in and measure again. You're not measuring the same material.
Yeah.
If that shear induced particle migration can happen and so on. So, but that could be an idea to go further. But at this point, yes, there's results available in literature, but there's not yet a consensus.
Okay, thank you. Okay.
One question I had in my mind since I started making the first Rheometer for my PhD thesis, is what is the slump limit where you can see you are measuring viscosity? Because I noticed that in your last test, the minimum slump was 230. Although in the previous one, we did concrete that were much less fluid. So maybe that was wrong to do this, but what is, I know there's no consensus, what do you think is a minimum slump so that you can start saying that there is a viscosity you can measure? Is it related? Because obviously we know that the less slump, maybe you're getting into like a material shearing or soil.
It's slump on itself is not going to tell the story. You got a slump of, let's say, 200 millimeters with a 0.55 water cement ratio, and you got a slump of 2 millimeters with a 0.2 water cement ratio. I'm much more confident on the 0.2 water cement ratio. Viscosity is much higher. So I'm much less likely to have a shear zone that's about this. The higher is that ratio. It's the ratio of yield stress to viscosity that really plays a role on how much material is being sheared. That's the one that plays. So slump alone is not going to do the thing, but you could combine slump with other parameters, and maybe the prime example, prime candidate could be a water to cement ratio to be reflective of viscosity, because slump doesn't measure viscosity, right? To make a guidance on that, and then it will depend on the device.
Put it the other way.
All right, gonna have exercise.
I know slump is not a good measurement for different things, but
even yield stress.
so we can say that the slump is a good indication of the yield stress. I think we all agree on this, maybe not, but anyway. So what is the minimum yield stress then, or the maximum yield stress where you can see that you can start measuring the viscosity?
It still depends on the viscosity. In my opinion, it's the ratio of yield stress to viscosity that's the determining factor.
Okay.
And then once you get to that, and that might be a suggestion for future research, because we didn't go that far, right? So we didn't want to have invalid results. Maybe a future campaign can say, hey, let's try to push the boundary, let's try to push hard to see how far we can go. But then once you have quality of measurement or validity of measurement as a function of yield stress to viscosity, then it will depend on the rheometry. The larger the gap, in my opinion, more parameters. The smaller the gap, less problems. But then there's other factors playing out. So it's going to be a complicated story no matter what.
Okay, thank you. Next one, Nathan.
Thanks, Dimitri. That was really great. Just to kind of build on what David was talking about, I think some of the consensus things that we have to talk about or think about are the applications that we're using it for. I mean, what kind of measurement of viscosity do you need to fill a slab versus moving through reinforcement? So just thinking about that might, there might be different ways that we need to measure those. And this is the difficulty, is that it starts getting kind of complex that maybe producers will be like, no, it's too much work to kind of do it. But that's kind of some of the things that we should think through. And then just a quick question, I like how you guys are trying to back calculate what's needed for that maximum. Any way that John Bolivar can get involved and maybe look at how that might have worked out from a computational standpoint? I mean, is that maybe just with some simple geometries, don't think.
I may have to talk with John, the issue is no longer in the it's no longer in the concrete industry, that's the sad part.
Yeah.
I can show it.
Yeah, first question. Go ahead. Go ahead, Dave.
And then we do have a question.
Small question.
Yes.
Yeah, go ahead, go ahead.
I don't need a second. Okay. Well, so on standardizing tests and finding your way, the community finding its way to standardized tests. Imagine you were around engineers 120 years ago, and they were all sitting around this thing called a slump cone. And someone said it should be 12 inches tall, someone said 14, someone said 6, someone said it should be moving on a rotating table. And so you have all these kind of different ideas about it. And at some point, the community finally says, enough of all this ridiculous discussion, we're going to just do this 12-inch cone. So that consensus has to sort of develop at some point, because it's somewhat endless to think that we're going to get the mechanics right item to item to item to item. They're going to be different. But for the equipment to have impact in industry, there should be some kind of a process by which there becomes a consensus. Right now, it's in somewhat a good situation that we're allowing all comers come up with your ideas. We don't want to prejudge it, but do we want to take as a community a process of weeding these things out?
So you're looking for a don't sit down yet. Because I have a question to answer your question, because I don't know exactly what you're looking. Are you looking for consensus in the equipment, or you're looking for consensus in the procedure?
Oh, excellent idea. I mean, maybe I can see what you were thinking. If you say consensus on the equipment, maybe you say, let the market decide. Throw all these things out there. More iCars are sold, so iCars become standard or something like that. Maybe.
That could be a market decision. That's out of our hands, although we have our preferences too. We should be careful that economics are not the main driving factor towards quality of equipment.
Well, everyone decides. I don't know. I mean, this is.
And on procedure, let me tell you this: that the procedure should be, in my opinion, I don't know if the group shares this, but in my opinion, it should be adjusted to the job. I don't think there would be uniform, standardized procedure to measure the of the product. To say you appreciate for that amount of time and that area for so many steps and so on. It needs to be adjusted to the material, because we have things that require more time. We have things, measurements, errors that require less time. So it's balancing. And sad to say that there might be certain mixtures on the market or certain concrete mixtures that cannot be measured. It just, before you reach equilibrium, it's segregated. So that's going to be a disaster. So there might be mixtures that you can't measure, and the procedure should depend on the material.